Hey, my name is Jimmy Daley. I manage the platform engineering team that builds all of the HPC platforms at Hewlett-Packard Enterprise. As Earl and the crew told you earlier, we lead the industry in delivering platforms. We have the broadest set of platforms in the industry. Not only do we have your standard x86 pieces, you'll see ARM platforms, AI platforms, big data platforms, big platforms, small platforms. There's a lot of stuff that we do. They asked me to come out and they said, go talk about things. I didn't want to give you a commercial on our platforms. Susan and I are here. If you want to talk about our platforms, we can talk about platforms all day. I want to talk to you about some of the challenges my team is having as we are designing platforms for what you guys are trying to go do with them. You know, they have a lot of good ideas, but the hurdles that are in front of us are pretty healthy. And the one I want to talk about today in primary is our nemesis, the active optical cable. Right? For those of you who don't know, these high-speed cables are the backbone of very large supercomputers. And the challenge that we have today is, although we all prefer to use copper cables, which are more costly, these active optical cables are becoming more and more a part of what we've got to go do. So I'm going to go through a few of these things. Even though these cables struggle with cost and a couple of other things, the adoption of these cables is certainly still very aggressive. We have to, in order to get our science done, build systems with these optical cables. The 50 gig, if you'll notice, we as an industry pretty much only use them sparingly. As we get to 100 gig speeds, we're already at about 40% of the mix in active optical cables. And as we move to 200 gig and beyond, we're predicting that most of what we deploy is going to have to be active optical as we move on. So if I talk about the challenges that come, first I want to start with cost. You'll see this is the length of the cable and the cost of the cable. If you'll notice a copper cable, this blue line, you almost miss it down here in the bottom, right? We can only get copper cables to go a few meters, and every time we move these things forward, it shrinks and it shrinks and it shrinks. Whereas the cost of an active optical cable is somewhere between 4 and 6x of a passive copper cable. And as we look, there are passive optical cables coming out, and that's the science and the technology that we as the industry are trying to roll together. So if I take this picture and show you this, I'm going to tell you these are list prices. I don't know anybody who actually pays list price, but assuming that the black magic they use to create the list price is consistent over time, this trend is unrefutable, right? A copper cable, right, was $150, now it's $500. I'm not sure that I'm even going to be able to do a meaningful 400 gig copper cable, which means I'm down on this line and I'm now at, you know, a list price of $2,000 for one cable. Go build a fabric out of that and see how far the wallet goes, right? It just doesn't work. If you look, the cost of the transport material, though, glass, is actually cheaper than copper. Here's the bad guy right here, right? It's all about this AOC. And to be frank, it's about the volumes, and there's a lot of business that goes into that as well. But my challenge, that's the wrong button. My challenge is there. By the way, I'm having the same problem on PCB design. So the actual printed circuit board itself, we're having signaling challenges. So again, if you'll notice these colorful boxes as they go, the bottom of the colorful box represents what I can do with the cheapest PCB material in the industry. And the top is if I go get the most exotic material in the industry, how far can I route PCI? That's what this is about. So over time, what this suggests is our signaling decreases as we move. PCI Gen 3, where we live today, right, I can get everything using, I'll say, fairly standard PCB material. As we start talking about PCI Gen 4, you can see that I'm going to miss this band that we call useful board routing lengths. We're going to start having to look at more and more exotic material. Now I'm certain we got a lot of smart guys at HPE, there's a lot of smart guys in the industry, and this orange box will shift up ever so slightly, but it will not shift up meaningfully, right? And my red box here is just a lost cause in a lot of this sense. So we are right now looking at, as we go to system designs for PCI Gen 4 and certainly for PCI Gen 5, what are we going to do to retool the way that we want to go after this stuff, and how do we make sure our system designs are ready to be prepared for this red box. Let me talk to you about some of these cables. I brought some props. This is a copper cable. A copper cable, right? We give you here a penny. The radius of a penny is 9.5 millimeters. This cable, which has 8 optical differential pairs in it, is the same as the radius of a penny, right? So you compare that with a 24 fiber, 12 fiber optic pairs, so 24 fiber cables, and it's, you know, the size of smaller than the size of a pencil, clearly. If I move through that, when you start to look at designing systems at a rack level, if I have 72 nodes within a rack, right, then I have 72 of these cables coming down one side of the rack, or half of that coming down one side and half coming down the other. As we start to build that out, I'm not building 72 node clusters anymore. They're 128 or they're 256. So coming down the side of each of the rack is either something the size of a CD-ROM, this is only 128, or something much closer to the size of a face of a watch, right? So there's a lot of that that's driving our system design as we move through. If I overlay it this way, one-to-one those cables, I get a 6x reduction in size just if I do one-to-one. If I look at the equivalent bandwidth, because the bandwidth in one of these cables is 4x and sometimes 6x the bandwidth of a copper cable. If I'm just looking for bandwidth, I get another 6x reduction in what we're doing, right? And then there's egress, right? I struggle with egress. Egress for us is one, how do I get this many connectors coming out of the back? If my switch has 24 ports out the back, can I get 24 of these in there? And would it be easier for me to get 24 of these in there? But I need egress for things other than fabric. In order for thermal solutions to really work, you need a lot of egress for air and other things. And so we are absolutely thermally challenged as we go into these solutions as well. Power-wise, so these solutions, a copper cable, the cable itself does not consume any power. 50 gig cable was 1.5 watts, and we're already looking at 5-watt cables. What this is the back of a switch like you saw in the previous chart. All of this power generates thermal. In a system design, what we want things to be planar, and we want them to be localized so that we can get our heating or our cooling solutions onto those pieces. And what we have with these active optical cables is neither of those. They're very hard for us to cool. They're very hard for us to get the egress. So I step through. If I move to passive optical cables, that also frees us up. Forget the economics and the physics and things like that. It frees us up. It frees you guys up to wire your data center one time, right? You put the wires in and the optics actually come with the thing that you're plugging it in. So if you buy the right glass, just think of the amount of dollars and manpower that you put into wiring up your data centers. It allows my engineers to design differently. Today, we are very driven to making sure that within a rack you hit the right switch radix, because if you leave switch ports empty, those are costs that have to get amortized across all the other nodes in the rack. and that becomes very, very painful. But if I move to optical cables where distances are, then I don't have a top of rack switch. I have a mid-row switch, and we just make sure that within that row, we design and get the right things there. So then I can start to design to power constraints and thermal constraints and some other things besides switch radiuses. But the biggest thing in my mind for larger solutions that this does is it allows us to start to optimize our topologies for the workload we're trying to go do, as opposed to optimizing for how do I get as many copper cables into this picture because I can't afford optical cables as we move through. So my time, I'm finished. All I want to say is we definitely know that in our designs, we're pushing real hard. There's been a lot of work in our labs. There's been a lot of work in the industry for midboard optics and all of the rise of photonics as they come around, right? I can tell you based on all the stuff I'm trying to show you here, now is the time for us to start that journey in real earnest. So I'm going to finish right there. Question?